All right, so for this lecture, we're going to talk about stochastic processes, which are which are a pretty abstract theoretical mathematical idea, but we're going to um, make them very applied. We're going to gloss over the theory as much as we can and focus instead on these sort of real life examples. The example that we focus on, kind of like our keystone example, is insurance related, but you could do a very analogous example in like the context of credit or finance, for example. Um, if you look at like the credit ratings of different companies' bonds, credit ratings of countries, even, right? These credit ratings like AAA, AA, that kind of stuff can fluctuate in a similar way to what we see in our insurance example. So it does have a pretty broad applicability. You could do an entire class, you could do entire classes on stochastic processes. I'm going to do my best to condense it down to, we'll see. I think I can do it all. I don't know, maybe like 200-300 pages of textbook in about an hour, maybe a little less. So yeah, so challenge accepted. Let's go. So if this is something that catches your fancy, if it is something you would like to dive a little deeper into, here's probably what I would consider the easiest, most accessible reference. This dude, Sheldon Ross, never met him before. He's a crazy guy. Just about every single book on probability models, particularly like stochastic process probability models, but also like more general probability models as well, is like written by Sheldon Ross, Sheldon Ross, Sheldon Ross. Like every book, every edition. Like I don't even know. Like I feel like the government should put should potentially intervene and like almost like break up this dude's monopoly. He's written so many books on stochastic processes. I will say, it's we're talking about probability, so it is a little 505-ish, and the vast majority, perhaps even the entirety of you have taken 505, but every once in a while someone takes a little bit of a more circuitous route and has not yet taken 505. I do think if that's the case, you will find certainly the majority of this still accessible. At some point, we'll calculate something referred to as a Poisson probability, but we'll use a software program to calculate those things. We won't do it like the more theoretical formulaic way.
So this is like a little bit of a mathy definition. A stochastic process X. So X just means a random variable, and then parentheses T, um, is a collection of random variables. The index T is often interpreted as time, right? So you have like X1, X2, X3, X4, right? And that just basically means where the process is at time 1 and time 2 and time 3 and time 4, right? So for example, it might be the number of defaulted loans at time T, might be the total amount of sales recorded by a supermarket at time T. Um, if this time index is countable, it's a mathematical term. We say it's a discrete time process. So, right, countable it's not a perfect mathematical definition, but usually we think of that the whole numbers. So, right, usually you'll be thinking like a T of 0, 1, 2, 3, 4. That's the typical discrete time process. We're not going to focus on it, but you can have continuous time stochastic processes where you measure time continuously, right? So it's not just 0, 1, 2, but like in theory 2.759132. Yeah, so like the third bullet point says, we're going to focus on discrete time processes. We're actually going to focus on a very specific type of discrete time process. one that's called a discrete time Markov chain, which we'll shorten or abbreviate to just Markov chain. All right, so consider a stochastic process indexed 1, 2, 3. And we're going to say the set of possible values for our random variable is also whole numbers. So 1, 2, so on to n. When x sub t equals some number I, what we're basically going to say is the process is in state I. Right, so I mean state I, it's going to be labeled as a number. It's going to be like maybe I equals 4. Right, and so that 4, right, maybe could actually mean 4. It could maybe mean, right, there are 4 loans that have been defaulted, or we have $4,000 left in our pension or something like that. But 4 could also be referring to a category, right? These processes are very general. So like we'll do some examples with like rain and sun, right? It could be 4 could be some type of climate, for example. Now, we're also going to assume that there is some fixed probability, Pij, that it will next be in stage J. So Pij is the probability that we go from state I to state J. Now again, I and J are numbers. So, right, you might see something like P24, which is basically saying the probability of going from state 2 to state 4. This, incidentally, is one of the defining characteristics of a Markov chain, right? And one of those is that the probability it moves into a certain state J depends only on its current state I, right? We could come up with lots of, I think, real life situations that are more complicated than that. So it is a bit of a simplification, but on the flip side, there are a lot of really interesting real life situations that are well modeled by a Markov chain. So this still is a very powerful thing to be comfortable with and learn about. So we could actually put these probabilities, these transition probabilities, into a matrix. And so the matrix looks something like this, right? So we don't do a lot of matrices in this class, but I feel like this is some notation we should be reasonably familiar with. So the first number refers to the rows, second number refers to the columns. If you're talking about the sort of how we kind of arrange things in a matrix, right? So we got P11, that's the probability of staying, I guess, in state 1, given that you're in state 1. And then we go across. P1n is the probability of going to state n if you're in state 1, and then so on and so forth. So let's do a simple example. Suppose that the chance of rain tomorrow depends on previous weather conditions only through whether or not it's raining today, right? That's an important assumption of a Markov chain. I'm no meteorologist, may or may not be a reasonable assumption. Suppose also that if it rains today, it'll rain tomorrow with a 70% chance, and if it does not rain today, then it will rain tomorrow with a 40% chance. We say the process is in state 0 when it's not raining, in state 1 when it is raining. So I believe on the next slide, I write out what that matrix looks like. I would encourage you to pause these slides and try to guess what it looks like. That is, again, the best way to learn is to do, not to watch, not to listen. So, right, I would encourage you to pause these slides, boom, hit pause. Write down what you think this matrix is going to look like. I'll give you a hint. It's a 2x2 matrix. And then unpause it and see if you're right. So hopefully that's what you got. If not, I would again encourage you to pause it. Hopefully you printed those slides so you can look at the numbers here and refer back to the description of the problem on the previous slide. right? We're basically saying, so what, we got state 0 and state 1. So that upper left-hand side is basically saying that if it's not raining, there's a 60% chance it will not rain tomorrow. The 40% chance is saying if it's not raining today, there's a 40% chance it'll rain tomorrow. And the bottom row is essentially the row of it raining today. So it's saying if it's raining today, it'll be sunny tomorrow with a 30% chance. It will rain tomorrow with a 70% chance. All right, so I guess it's nice. I mean, a lot of textbook examples, there's a ton of textbooks examples that have rain, and then you get into this like crazy umbrella problem where it's like, all right, if you if you take an umbrella from point A to point B, what's the probability that you're going to get rained on? Like, textbooks love rain and not rain and umbrellas, right? But it's not clear to me how useful like those types of examples are to like business. So here's a slightly maybe more interesting example. Although as we can see, it's a lot of words. So in most of Europe and Asia, annual insurance premiums, so how much you pay a year for your insurance, I guess say car insurance or yeah, I guess we'll go car insurance. They use what's called a bonus malus system. So that's Latin for good and bad. Each policyholder is given a positive integer valued state, and how much they pay is a function of that state. Also included is like the type of car, the type of policy, the deductibles they want, and other stuff. So that's why we say it's a function of that state. A policyholder's state changes from year to year in response to the number of claims, right? So you can think of claims as like number of accidents. So if you don't have any accidents, right, probably your state will improve. If you have a lot of accidents, your state will probably get worse. And high states are bad, low states are good. Does that make sense? So for a given bonus malus system, let SIK denote the next state of a policyholder who was in state I in the previous year and made a total of K claims in that year. If we suppose that the number of yearly claims made by a particular policyholder is a Poisson random variable, so this is where, right, if you haven't had 505, you might be like a little bit shaky. With parameter lambda, then the successive states of the policyholder will constitute a Markov chain. That's something we could prove. So there are usually many states, right? We might imagine 20 or more states is not unheard of. But the following table is very typical, albeit slightly simplified just to keep the math a little bit more palatable. Right? So this is like a common system, right? Just 4 states. Remember, the lower the state, the better. So of course, right, if your number 1 is the best state means you have the lowest premium. You're a quote super safe driver. And then, right, where you go depends on the number of claims, right? So if you're in state 1 and you have 0 claims, you stay in state 1. Now notice, like for example, there could be multiple claims that send you to the same state. So like look at state 3. If you're in state 3, you pay $400 a year. If you have 0 claims and you get to improve your state, you get to go to state 2. But if you have anything other than 0 claims, you go up to state 4. So I guess state 3 is almost like a probationary state, it looks like. Does that make sense? Okay.
All right, so here is our transition probability matrix. The notation's maybe a little bit unusual. It's consistent with like the reference book that I mentioned in the earlier slide. So that A sub 0 is basically saying that's the probability of you having 0 claims. And that A sub 1 is the probability of you having 1 claim. that A sub 2 is the probability of you having 2 claims. And then 1 minus A sub 0 minus A sub 1 minus A sub 2 is the probability of you having 3 or more claims. So a couple observations. First off, I apologize for this larger matrix. I couldn't quite get the parentheses to work, so we have a naked matrix. Matrix without its parentheses. So hopefully that's not too scandalous for you. And second observation, I don't know that we stated this explicitly before, but it's a math fact and hopefully an intuitive one, that for any transition probability matrix, if you sum the rows will always add up to 1. And that's the trick that I use to derive that rightmost column. So the rightmost column is always 1 minus everything to the left of it, because I know that all those probabilities have to sum up to 1. So again, hopefully that makes sense, right? Basically that first row is, right, the probability of 0 claims, and then the probability of 1 claim, and the probability of 2 claims. And so the probability of 3 or more claims is 1 minus the probability of 0 claims, minus the probability of 1 claim, minus the probability of 2 claims. So take a few moments, scroll back and forth as needed to make sure that you can kind of see like where all these things are coming from. It's something that should hopefully make sense to you, and if not, feel free to pause this thing and shoot me an email.
Okay, so that kind of just sets up a slightly more complicated, but I think more useful type of bonus malus matrix that could model something in the real world. Now, where do we go from here? Well, there's something called in-step transition probabilities. So if we define Pij to the power n to be the probability that a process that is in state I today will be in state j after n time periods or n transitions. Now again, you could prove this. It takes quite a bit to prove it. We're going to just accept it. That we could find the in-step transition probabilities by taking our matrix and just raising it to the nth power. So taking that matrix, like if you want to take it to the second power, you just take the matrix and multiply it by the matrix. And here we're talking about matrix multiplication, which you may or may not be familiar with linear algebra, but it's different than just component-wise multiplication. So let's see what a two-step transition matrix would look like for our rain example. So here it is in R. So first I have to actually put the matrix in R. So here I'm creating a matrix called rain. That's the syntax that I would use to create it. Then I just type the word rain. It'll actually pull up the matrix so I can make sure I inputted it correctly. And then the syntax to do matrix multiplication is %, asterisk, %. That does matrix multiplication. If you do just the asterisk, that will do component-wise multiplication. So what do I mean by component-wise? I mean that upper left number will be 0.6 times 0.6, so 0.36. And that upper right number will be 0.4 times 0.4, which would be 0.16. Right, that is not how matrix multiplication works. And again, you may or may not be familiar, you may or may not have taken linear algebra, but at the end of the day, it doesn't matter, right? Because we can have R do it for us. And so we see what those are. Also notice those numbers, those probabilities, if you sum across the rows, still sum up to 1. So what are those numbers saying? That top left is state 0, so it's basically saying that if it's not raining, if it's sunny today, the probability that it will be sunny 2 days from now is 48%. The probability it will be raining 2 days from now is 52%. Easy enough? We could also do matrix manipulations in SAS through proc-IML. So proc-IML, there's a lot to it. It is a useful skill to have. I've seen job postings that are looking for proc-IML. Proc-IML is like a little bit more of like a programming-based language, a little bit more like R, I guess. It's used a lot for doing like matrix manipulations. I forget what the IML stands for. I think the ML might be like machine language, maybe like interactive machine language, something like that. I wouldn't swear to it, but we can see the syntax is actually relatively simple, right? I set up some matrix P, and then I can create this P2. That P2 is just my abbreviation for P squared. And it's just P times P. So actually in proc-IML, the asterisk does mean matrix multiplication. And then you could print it, right? And there's our 4, 8, and 5, 2. So show you how to do it in R as well as in SAS. Okay, so that's the in-step transition probabilities. Why do we care about those? We care about those because they let us figure out unconditional probabilities. So this uses just like some very basic fundamentals of probability. Even if you haven't taken 505, like, I mean, the notation, I know the notation's like a little bit crazy, but like the actual, like the probabilistic rule that we're using is like something you would learn in like a Math 121. So let's define alpha 1, alpha as in the beginning, right? So that's the probability that X, right, our Markov chain at time 0 is in state I. So it's kind of like the probability that our chain started in state I. Alpha I is the probability started in state I. Then, if I want to know the probability of X sub n equaling J, the probability that I'm in state J at time n, well, that's just going to be the sum. And again, this is like a pretty basic probabilistic rule, and hopefully is like a little intuitive. That's the probability, the sum of the probabilities that X ends at state J and that it started at state I, right? So it's basically like, imagine 3 states. It's like basically saying the probability that like at time 10 I'll be in state 3 is the probability that at time 10 I'll be in state 3 and I started in state 1, plus the probability at time 10 I'll be in state 3 and I started at state 2, plus the probability at time 10 I'll be in state 3 and I started at state 3. Right now, we know it's like a probabilistic fact that the probability of A and B is the probability of A given B times the probability of B. So I'm just applying that rule. Right, but the probability that X sub n equals J given that X sub 0 equals I, that's just the in-step transition probability, right? That's just Pij to the power n. And then that other piece, the probability X0 equals I, is alpha I. Right, so this gives me unconditional probabilities. What do I mean by that? We'll see in a word problem in just a second. Okay, so yeah, so let's say that we will be arriving in our example area, right, our little beach area for vacation in 1 month. What is the probability that it will be raining 3 days after we arrive? Right, that's what I mean by unconditional. Like, I want to know what's the probability it's going to be in a certain state, but I don't know what state it starts in. It turns out I can solve problems like that, right? I can solve the probability of ending in some state at a particular time even when I don't know what state it's starting in. That's what I mean by unconditional probabilities, right? Why do I care about 3 days? Well, that's when our beach trip is planned. Now we do need those alphas, right? So sometimes those alphas might just be thought of as like relative frequencies. So, right, maybe 40% of the time it rains. So that means that, I guess we're saying our states are 0 and 1. So I guess that means that alpha 1 would be 40% and alpha 0 would be 60%. So those derive our alphas. So I want to know the probability in 3 days. So that's, I got to take that Pij and raise it to the power 3, multiply it by itself. Well, I guess 2 times, but right, 3 of these matrices all multiplied together. And you could use the same syntax that I already showed you in R or proc IML. So this is what like that initial matrix raised to the power 3 looks like. Now we don't need all of those numbers. So again, it'd be nice to refer back to this. So hopefully you have this printed out so you can look at it. I'll show you which numbers we take in the next slide.
All right, so the calculation, basically works like this. There's two possibilities. There's 2 options. The first option is that when we get to our vacation spot, one option is that it's not raining, and there's a 60% chance of that happening. The other option is that it is raining. There's a 40% chance of that happening. All right, so those are our 2 options. 60% chance it's not raining when we get there, 40% chance it is raining when we get there. That's from the formula 3 slides back. Now, I apply the matrix that we derived 1 slide ago. And that matrix that we derived 1 slide ago basically said that if you're in that state 0, if it's not raining, then there's a 56.6% chance it will be raining in 3 days. That matrix also says if, on the other hand, it is raining when you get there, so state 1, then there's a 58.3% chance that it will also be raining 3 days from then. And so we do those calculations, and we end up getting 57.28%. Pretty cool, right?
Okay. Last set of concepts. And that is this idea of classification of states. So state J is said to be accessible from state I if Pij to the power n is greater than 0 for some n. So, right, it's accessible. Maybe it can't get there in 1 time period. Maybe it can't get there in 2 time periods. Maybe it takes a while to get there. But as long as it's possible to get from I to j, we say that state j is accessible from I. And if 2 states are accessible to each other, then we say they communicate. And then that has this transitivity property associated with it, which should be intuitive. If I communicates with J and J communicates with K, then I and K also communicate. Two classes that communicate are said to be in the same class. And so why do we care about this? Well, we care about this because a Markov chain is said to be irreducible if it consists of only one class. That is, all states can communicate with each other. And in terms of proving something like that, that transitivity property on the previous slide is helpful. So insurance example, right? Again, you're gonna have to kind of backtrack to that insurance example where we had like all the A's, the A0s, A1s, A2s. But if you kind of trace through that and look at it, you should be able to find that it's irreducible, that any state can communicate with any other state. So our insurance example is an example of an irreducible Markov chain. Finally, the last thing that I want us to talk about is this idea of limiting probabilities. It turns out that under certain assumptions, if we look at that in-step transition matrix for larger and larger values of n, right? We look at 10 time periods in the future, 20 time periods in the future, 30, that it actually starts to change very little, as if the probabilities are converging to some numbers. These numbers are called the limiting probabilities, and we could think of them as the percentage of time that a process spends in a particular state. Now, this is why we care about this irreducibility. If we have an irreducible Markov chain, then we could prove that the limit of Pij to the n exists, and it's independent of that I where we started at. Furthermore, right, if we want to denote pi j as that limit, then we can show again mathematically that pi j is just the sum over all the pi's times the one-step transition probabilities. So, why do we care? There's a lot to this example, but I mean, that's what makes it interesting, right? So I do hope that you're taking the time. I mean, I know I'm talking about it relatively quickly. Probably you're gonna have to sit and really think about it, particularly where I transitioned from that table of premiums to that like transition probability with all the A's. But hopefully if you meditate on it, you can figure it out. If not, right, I'm only an email away, but that's definitely one of those things where like being in a classroom environment where I could interact with you and we could talk back and forth and I could maybe do some additional work on the board, I think would help. But I'm confident you could figure it out if you kind of think it through. Anyways, we're going to continue with that example. What is the average annual premium paid by a policyholder whose yearly number of claims is a Poisson random variable with a mean of 1/2? So, right, that lambda is 1/2, which means that we could now solve for those A's.
All right, so if I know that the claim probabilities follow a Poisson distribution with a lambda, you could think of the lambda as the mean. So with a mean of 0.5, so on average, we're saying a person files 0.5 claims. Then I can calculate those probabilities. In Stat 505, you learn a very specific mathematical formula. You may or may not remember it. You may or may not have taken Stat 505. Regardless, we can use R. You can use SAS as well to calculate these probabilities. In R, you'd use the d Poisson function, so the probability d for density of a Poisson function. So that first number tells you what you want the probability of. That second number tells you what the lambda is. So I'm going to calculate A0, A1, A2. I take a look at them, right? A0 is 60.6%. So there's if lambda is 0.5, there's a 60.6%, right? There's more than half a probability, or more than half of a percent chance, or more than half of a probability that a person will have 0 claims, 0 accidents. there's a 30% chance they'll have one accident, and there's a 7.6% chance they'll have two accidents. And then, of course, we can see it's rare, it's unlikely they'll have three or more accidents. I can get that, of course, by adding those three numbers up, which would give me about 61, 68, 68.6-ish. So that would be about like 1.4-ish% chance of three or more accidents, right? So now I take these numbers, 60, 30, and 7. I go back to that transition probability where I had A0s and A1s and A2s, and I just fill them in with actual numbers, and I get...
Right, here's what it should look like. So I'm going to take this matrix right here and show how we apply that formula. So I had the formula for calculating those limiting probabilities, and it maybe looked a little crazy, but it's actually pretty straightforward. You actually just, we have this pi 1, pi 2, pi 3, pi 4, right? We could think of pi 1 as like the percentage of people that are in state 1. And we could think of pi 2 as like the percentage of people in state 2, and pi 3 as the percentage of people in state 3, and so on. We set our formulas up by going down the column. So what we're basically going to see in the next slide, and I'll talk it through this slide so we could see, the way that formula basically works is we're going to say pi 1 kind of corresponds to the first column. So pi 1 is going to be pi 1 times 0.6065 plus pi 2 times 0.6065 plus pi 3 times 0 plus pi 4 times 0. And then second column, pi 2 is equal to 0.3 times pi 1 plus pi 2 times 0 plus pi 3 times 0.6 plus pi 4 times 0. You get the pattern? And then pi 3 is going to be pi 1 times 0.07 plus pi 2 times 0.3 plus pi 3 times 0 plus pi 4 times 0.6. And then pi 4 is pi 1 times 0.01, pi 2 times 0.09, pi 3 times 0.39, plus pi 4 times 0.39. So I think I put all this in the next slide. Yeah, right. So that's everything that I said basically. That pi 4, you can see, gets a little lengthy and the typesetting got a little messed up. Sorry about that. We also have that extra constraint, right? We have a fifth constraint, and that is that all probabilities sum to 1. And so what do we have? We actually have what? We have 4 unknowns, pi 1, pi 2, pi 3, pi 4, and 5 equations. So we actually have one more equation than we need. So that means actually probably the lengthiest equation is that pi 4 equation, right? So if we only need 4 of these equations, that would probably be the one I would drop. So I could use that pi 1, pi 2, pi 3 equation along with that final equation that says that all probabilities add up to 1. And so now we have to solve for the pi's. We could actually do that in ProcIML. So ProcIML, so each of those lines is referring to an equation. So that negative 0.3935 and that positive 0.6065 is referring to that first equation that we had. You might say, well, what the cut though? Where's that negative coming from? Well, we have to set these equations up. Well, we don't have to, but it's simplest to set these equations up. No, I guess we do have to. Where all the pi 1s are on the same side of the equation. Remember, our equation was pi 1 equals 0.6 times pi 1. So we actually had pi 1 on both sides of the equation, so we have to fix that. So if we subtract pi 1 from both sides of the equation, now we have basically 0 equals negative 0.3935 pi 1 plus 0.6065 pi 2 plus 0 pi 3 plus 0 pi 4. Does that make sense? Incidentally, right, I say 0 equals all blah, blah, blah. If you go down and look at the C equals, the first term of that is 0. So what do we have? The A construct, the A is a matrix. Every row corresponds to one of those, to one side of one of those equations. And the C, the vector C, corresponds to the other side of the equation, right? So for the second thing, what did we have? The second equation we had was pi 2 equals 0.3 times pi 1 plus 0 pi 2 plus 0.6 pi 3 plus 0 pi 4. We have pi 2 on both sides of the equation. We need it just on one side, right? So I subtract pi 2 from both sides of the equation, and now I have 0, right, which is the second term of my C vector, equals 0.3 pi 1 minus pi 2, or minus 1 times pi 2. Are we starting to see it? Plus 0.6 pi 3 plus 0 pi 4. And then the last one is what? We got 1, 1, 1, 1. That's pi 1 plus pi 2 plus pi 3 plus pi 4. And that sum equals 1, which is why that we have a 1 there for the last element of C. All right. So that we can think of that A matrix as one side of the equation. It's the side of the equation where we have all the coefficients that are multiplied by our pi's. We can think of the C as the right-hand side of the equation. And then, right, I can create X, which is the solution to these things, and then print X. And then if I do that, those are the numbers I get. Pretty cool, right? So it's basically saying that 36, I guess I'd round that to 37% of our customers are in state 1. So that's good. I guess we have a good clientele base, right? 37% of our customers have this sort of good driving record. 24% of our customers are in state 2. 21% of our customers are in state 3. 18% of our customers are in state 4. Yeah, pretty cool, right? Now, of course, we're still not there, right? We still wanted to know, what's the average premium that we would expect? So that's one last step. Let's do it on the next slide. So the average premium paid is, well, 36% of our customers are in state 1. People in state 1 pay $200. Right? 24% of our customers are in state 2. If you're in state 2, you pay $250. 21% of our customers are in state 3. If you're in state 3, you pay $400, and so on. So we calculate that expected value, and we get $326, right? And so that's pretty cool, right? I mean, there's a decent amount of pretty complicated math that takes us from, right, something very concrete, right, which was what? It was just the table of premiums, right? I guess an assumption that the number of claims follow this Poisson distribution with a certain lambda. And then, right, just this stochastic process logic leads us to this kind of average premium, right? That average premium is what would drive us for like figuring out, right, how much money we might expect to make, whether or not that premium is sufficient to like meet our overheads, right? It's all types of questions that we could use whose answers might depend on that $326. Right? Pretty cool, right? I intentionally kept these slides a little bit on the shorter side because the math is maybe a little bit more than kind of like right? An average lecture in our program. It does feel more 505y than say 512y. But I mean, I do think at the end of the day, we came up with like a very applied, very useful number. So hopefully, right, that made it feel like something useful to us. All right. I already talked about how bittersweet this last set of PowerPoints is. I promised myself that I wouldn't cry, and so as I feel myself tearing up right now, I'm going to go ahead and end these PowerPoints.